Hello, EDUCAUSE 2020. My name is Carl Grafe. I'm a data analyst at Brigham Young University-Idaho in Rexburg, Idaho. And I'm going to be speaking today on no black box, intuitive targeting using available data and simple math. And the inspiration for this presentation I'm going to be giving has to do with targeting, artificial intelligence, algorithms, predictive analytics, a lot of the buzzwords that we've heard not only in higher education, but in many other sectors. But within higher education, I feel like it's really starting to take off. Just last month, there was an article on the EDUCAUSE blog called Improving Student Success with Machine Learning. And you can see a couple of lines here. Imagine students could achieve what they could achieve if they were provided 24/7 support, could spend more time with their advisors, have access to expert knowledge guided by intelligent technology tools. So there's this vision of student success, and yeah, there's a lot of potential there. We started to dabble in some machine learning here at BYU Idaho and plan on moving more into that area in the future. But there is the big, elephant in the room hanging over this area, and that is the black box, right? Like, not only do you need the kind of expertise just to develop these kinds of models, but a lot of times understanding what's going on behind the scenes is impossible in some cases to explain to humans. And that's not true for all models, of course, but that's something that limits some of the operational aspects of it. So I'd like y'all to take a minute. I'm going to put up a poll question. I'd like y'all to think about the question and to answer always, frequently, rarely, or never. So here's the question. So the question is, if you were building models to predict student behaviors, how often would it be important that the model be humanly understandable or explainable? And this question was presented over a year ago on the Katie Nuggets machine learning website. And the results that they got were 37% always, 48% frequently, 13% rarely, and 2% never. So if you said always or frequently, you're in good company. And of course, as I was saying, while most machine learning developers want this, it's not always available. Here's a quote from an article in Electronics academic journal, and I'll give you a second to read these. Feel free to pause the video if you need to, but it's just making the point that for a lot of the models that are being used today, especially the ones that are getting more sophisticated, it's just not even possible to explain in human terms. And this affects, the development of the model, but also the implementation of the model, and also the ability to turn the results of the model into actionable interventions. And it just throws that extra hurdle in each of those processes. And there's a lot of interest in making it more explainable, making it more accessible. If you look at the search words, machine learning interpretability on Google Trends, you can see that there's been a bit of an uptake in the last couple of years as there's more interest in research in this area. And again, all this isn't to say that it's bad or that there's even necessarily a need. It may just be that we need to get more used to not having the back-end view of what's going on with these and just accept the outputs. But this is something that's a real issue. And at BYU Idaho, we were thinking about what are some ways that we could use the data that we have to answer some of these questions and have it done in a more explainable, interpretable way. And we asked this question, before a student's first day of class, what do we know about them? What data do we have And of course, you know, we get some demographic data from the application from the students. We have their academic history potentially, you know, high school GPA, maybe some standardized test scores. If they had any transfer work, we might have some of that information. But I mean, I'm sure you can imagine that there's going to be a lot of missing data, and we're not going to have this on every student. Another thing that we might have a little bit of a more complete picture on is their student profile information. So for example, like at BYUI-Idaho, we require them to declare a major on application. So we'll have that for every student. We might have some housing information on them. We're going to know if they're on campus or off campus, that kind of information. And we'll know their class schedule, of course, right? That's the reason that they're at the school is to take their classes, and that's something that we control, and we know where they're planning on going as far as registration goes. And this was a piece that was really interesting to us because it's so closely tied to student success as far as their academic performance goes, right? And so that's something that we really wanted to look closer into and see what kinds of predictions we could make from that information. One thing that occurred to us is we can potentially, I mean, this is something that we're experimenting with, right? But we decided to go ahead and use 5-year pass rates to get what we were calling the rigor of a course and get an idea of, you know, how hard is it to pass a given course based on how often students, you know, pass or don't pass over time. And one thing that was useful as far as the work that we're doing here goes was that you can treat that 5-year pass rate as a probability. And here's a few, I won't go into too much detail on these, but just some probability rules that ended up being useful for us in this. First of all is just that if you want to have the probability of 2 events happening, so like the probability that a student passes Class A and Class B, then you can just multiply those probabilities together if they're independent events, which we're going to be assuming here. And then there's also this idea of expected value, where we can treat the probability as a measure of like a count over time, potentially. So if we want to know how many classes a student would be expected to pass, we could add up the probabilities of different courses. And you know, there's the linearity of expectation, which just means that we can add those probabilities and have it mean the same thing as adding up the expected values. And then subtraction, which just allows us to get the opposite side of the probability just by subtracting from 1. So let's look at the scenario where students taking courses A, B, C, and D this semester. And we've got the 5-year pass rates for these courses: 92%, 88%, 95%, 91%. With that situation and using the formulas that I just went over, we could look at the probability of the student failing at least 1 course just by taking the probability that they pass all the courses and subtracting that from 1. And of course, the probability of passing all the courses is just going to be the probability of each of those courses multiplied by each other, the product. And once we do a little bit of algebra there, it works its way down to 0.3 or 30% chance that they're going to fail at least 1 course based on those 5-year pass rates, right? And that particular combination of courses in that semester. So it's only based on those 2 things, which is useful, of course, but it doesn't tell the full story, right? There's more you know, that determines whether or not a student's going to pass and fail than just, you know, what happens on average. This might be true for the average student, but of course not all students are average. If we look at fitting a low S curve through these data, you can kind of see what happens as far as the prediction on the x-axis. As it increases, the observed actual passing or failing for these students, which is the campus students from fall 2018 at BYU-Idaho. You can see that the trend, you know, increases as the predicted score increases, but it doesn't line up. And the students that are at the highest risk of failing off of this model are just kind of a coin flip as for whether or not they're actually going to fail. So we saw these results and thought, there's a piece that we need to add to make this more realistic, more usable. And so consider the same scenario that we were just talking about, where students taking those 4 classes. But let's look at a different set of classes that they've taken in the past, and say they've taken 6 classes before this semester, classes A, B, C, D, E, and F with the pass rates that you see there. And suppose that they only passed one of them. And can we use that information to get a better idea of the likelihood that that student's going to fail at least one course this semester? And we developed what we call a pass weight, which is just the observed number of passed courses divided by the expected number of passed courses. As I said, we can get from just adding those 5-year pass rates together and treating them as an expected value. And if we don't have enough data, so n less than 5, we're just setting it to 1.0, so it doesn't change that previous probability. So, but we could just do some algebra there, add those expected values together, take the one pass course and divide it by that sum, and you get a pass weight of 0.175. When we apply that to the probability of passing all their courses, it's just discounting it based on their historical academic transcript, basically. And students that exceed the average pass rate are going to be benefited from this, and students that fall below are going to be discounted. But again, you can just multiply those probabilities together, do some algebra, and you can see that it increases that 30% chance of failing to an 88% chance of failing for this student. And when we fit the lowest curve through that data, you can see that it is a much more almost linear trend as the predicted likelihood of failing increases from 0 to 100%. The observed probability increases almost right along with it from near 0 to 100%. You can see that it dips a little bit in the middle, and so there's a little bit of miscalibration there. But when you consider the limited amount of information that is going into this and how this is all information that should be available for almost every student, it's pretty remarkable. So this is what the report that we built looks like in Report Builder. It's a SQL Microsoft product. And you can see here the students at risk of failing one or more courses in fall 20. I've got the current semester brought up here. You can see the identifiers and the names of the students, and emails, and cell phone is all de-identified, but this is real data. And you can see the way that this works is the advisor goes into this report and they can look at this list of students, all the students in their college. We've got our advising split up into different colleges, but they can see the cumulative GPA of a student, how many credits they're currently enrolled in for this semester, so fall 2020 in this example, how many prior attempted courses they've had, how many they passed, a lot of the information we've been talking about, how many they should have passed. So like this student, you can see they've taken 6 courses, didn't pass any of them. Should have passed 5 of them just based on the pass rates. And so using all that and running it through the formula that we had set up, you'd expect a 58% chance of failing for this student just based on the pass rates for those 7 courses. If you factor in the pass weight for that student's individual academic history, that 0 out of 6 courses compared to 5 out of 6, it bumps their probability of failure up to 100%. Now, of course, a student is never really 100% likely to fail, right? Because there's always a chance that you can get a student to where they need to be. So this isn't being used that way to say, oh, there's no point with this student. This is being used to say, who's at highest risk of of failing at least one course this semester. And see here on the right, we've got a sub-report that goes to students' actual schedule. And so for this anonymized student, in this sub-report, we've got their high school GPA, ACT scores, just a little bit more information about them. This history goes to another sub-report that pulls up their full transcript. And I don't have a de-identified version of that, so I won't pull that up, but it just gives a lot more individual detail about that student. Then it gives what those 7 courses are that student's enrolled in this semester. And if you look at the schedule, while it's a lot of courses, none of these are super low on the pass rate, except for maybe this introductory math course. But what this allows the advisor to do is to go in and say, you know what, I'm going to call up this student and we're going to talk about this, because maybe this isn't a crazy schedule, but based on their academic history and the fact that they have tried at least one semester before, and I'd be able to go in and look at exactly what their circumstances were. But the fact that they haven't passed any courses, I'd want to talk to them. And it may be that it was just a fluke semester, last semester they had some personal difficulties or something that prevented them from being able to pass any of their courses. But it could also be that they just weren't up to it. And the advisor could say, you know what, let's take that guitar class and maybe that marketing class, and let's put them off to a future semester, and let's try maybe just 4 or 5 courses next semester and see how we do with that. And then maybe we'll try a little more the next time if you want to. And so you can kind of see the power here. This isn't telling the advisor how to do their job. It's just a tool that gives them the students that are maybe at the highest risk just based on the classes that they've registered for and their academic history, and giving the advisors that those people rising up to right up to the top, so that they can just work down the list and try to see if there's room to help these students to maybe adjust their schedule a little bit. And this would typically be done during the registration period, of course, so this is going to be most useful up to about a week into the semester. And so we'd want to look at other tools for beyond that. Another thing that's really nice here is we've got it set up so that you can go back to previous semesters. So like, let's go back to spring 20. And we can see what the accuracy was. So like in spring, we predicted 998 students would fail, ended up being 1,002. And these aren't all the same, of course. So the actual accuracy for probability greater than 50% actually leading to failure, or probability less than 50% leading to not at least one failure, that accuracy is about 76% for these students. Which again, considering the limited amount of information that we're putting in here, and then it's all information that we have readily available, is pretty remarkable. So we actually started this intervention in fall of 2019, so a year ago. Like I was saying, they did it during registration. The advisors just, as they had time, between working with students on resolving scheduling issues, other scheduling issues, they could take a minute and call up a student and say, hey, I noticed that you're taking, 8 courses this semester or something, and I was looking at your past semesters, and it looks like that might be a bit much for you. And anyway, the advisors would have total freedom to approach it however they wanted, but they'd be starting at the top of that list. And I think you probably could see on that report that you can sort by different columns. So if they wanted to just look at the student schedule and ranking students that way, they could sort off that column. If they wanted the one that's a little bit more predictive, they could go off that one, but it might be a little harder to intervene in a student's academic history, because that's been done already. But the current semester, there's a lot of room for improving a student's schedule potentially. So we did look at minority students. We didn't do any direct targeting in this initial pilot phase. But when you consider that our minority students are more likely to be first-generation students, more likely to have language barriers, a lot of these things that directly impact their ability to schedule their course load in a given semester, in a way that maybe even fits what they want, just due to lack of experience or lack of understanding. We would expect that they would benefit more from this kind of intervention. So when we did some basic evaluation of our pilot run of this, the accuracy for fall 2019 was 74%, and we did see a modest decline in our overall institutional failure rate, but it's unclear at this point, just how much of that may have been attributable to this program. We have a lot of other interventions that we have going to help students to not fail and to do well in their classes. When we applied this formula retrospectively to previous semesters, it was always in that kind of low 70s level of accuracy. And with our pass rates, probably averaging, 85 to 90%, you could just, if you just said, let's assume that every student is going to pass all their classes, you could get, 85 to 90% accuracy. But the value here is that we're able to identify those students that are more at risk. So I don't have the numbers here, but when you draw that line at 50% probability in the prediction, you do end up having a somewhat lower positive predictive value. So the likelihood that a student that we predicted was going to fail at least one course actually did is somewhat low, but the sensitivity was fairly high for that level. And then as you increase, of course, it just depends on where you draw the line. But as you increase that probability in the prediction to those higher risk students, the sensitivity declines because we're not going to catch as many, but the positive predictive value goes way up. So it's a balancing act, but we decided to just look at that 50% cutoff for now. But the advisors are starting at the top of the list, so that's those students with the highest positive predictive value. So again, with the prior semesters, the accuracy was similar. With the minority students, we did find that they were somewhat more likely to be identified as at risk of failing than the white students. You can see at 31% versus 25% for fall 2019. But the failure rate for minority students declined at a similar amount compared to the campus-wide rate. So, of course, the biggest question with an intervention like this is do the users like it? Are they willing to use it? And our advising department has continued to use this tool since fall 19, and we have plans for doing a more thorough evaluation and really get down on what the effect size is for this work. But it seems to have been helpful to them. Again, it goes back to that explainability and interpretability. Like they know what numbers are driving these predictions, and they know what levers they have to influence those numbers. And there's a lot of power in that. And so we, I guess just recommend making full use of that opportunity. A few takeaways, think about explainability in whatever modeling approach you may be using for targeting students for student success. Use the data that you have. Again, it's just you making full use of every opportunity that you already have. And think outside the box, not just the black box, but think about ways to use what you have in new ways to get meaningful results. Thank you all for your time, and I'm happy to respond to any questions or anything if you contact me. outside of the presentation, there's some tools in the conference website and other resources. But thank you for your attention and best of luck.